most useful things are the step function and the ramp function. Okay, and two more things that we will find, especially for beam problems. These will be extremely useful. Okay, so you got this idea, right? So we got two more things. One is concentrated loads. If you have a concentrated load like that, let us say 10 kilonewtons, acting at a location x equal to 7. The way we are going to write it is x minus 7 10 to the power minus 1. So this is not power like in polynomials. This tells me it is a concentrated load. By the way, this material is very briefly covered in Shigley's book. This is in chapter 3. It will tell you method of singularity functions. I think it's chapter 3-5. So please take a look at it, and they will list all these things in a very brief way. They won't actually do any exercises. They plunge directly into doing the problem. So please remember, you have to kind of practice it a little bit in order to do more complicated things. Okay, but this thing is there in Shigley, section 3.5, and again in section 4, when they talk about beam deflections by singularity functions. So those two things I'm combining here and giving it as a tutorial with more detail than what is available in Shigley. Okay, so this is concentrated load. The next thing is a concentrated moment. So if I have like this, concentrated moment, torque, I will write this, let us say 10 Newton meters. I will write it as 10 times, let's say at the same location x equal to 7, x minus 7 to the power minus 2. This means concentrated moment. Okay, so now we have our list: concentrated load, concentrated moment, load jumps pointing up. This will be written as again 10 Newton per meter. Load jumps will be written as 10 times x minus 7 to the power 1. Sorry, to the power 0. This means constant load distribution. And then ramp will look like this. Let's say the slope is 10 Newton per meter squared. You can see that gradually the meter level comes down. See, this one is kilonewtons, then it is Newton meter, Newton per meter squared, and this one is 10 x minus 7 to the power 1. This tells me ramped up load. This tells me change in slope or jump in slope. This tells me where it is. So you say, okay, this was fun, or maybe it was not, I don't know, but I hope it was fun for you, because it's a very powerful way of describing. So you have converted any kind of straight line graph function like this, fairly complicated straight line graph function, into a representation. Why is this powerful? Why is this useful? One, it can be completely computerized. What can be completely computerized? Calculation of shear force, bending moment, y and theta can be completely computerized if you know how to do it. In fact, you can do it in Excel. So what I mean by that is this: your task actually is only two things. You have to find this. I told you last class there are two things that were kind of tedious, right? Doing the integrations that you can computerize because we have standard fixed ways of doing integration, because it's exactly like integrating polynomials in an explicit formula. Second thing is doing all the algebraic solutions for finding boundary conditions. So those two things are the only two things that the computer can do. You have to do the other stuff, assigning boundary conditions and actually being able to figure out what is Q of x. Okay, so that's the real power of this. So I want to show you this power. So let's look at a specific problem. So we have the following problem. I have a simply supported beam. Okay, and I have a distributed load. That's the problem statement, and I have, this is, let's say, half a meter. This is 1 meter, and the load is 1 kilonewton per meter. Okay, we want to solve this. So step 1. Use singularity functions. To represent the external. Okay, between the two supports, between the two ends. This is a very critical idea, so I want to make sure that I am not including this thing and I am not including that. Okay, the two corners, tips of the beam are not included. Okay, the x equal to 0 and x equal to L are not included. This is different from the way the book does it. The book actually asks you to include it. I personally think it's a bad idea because it will confuse how the boundary conditions are applied and how to use it. If you do it my way, you will always have to do the same thing irrespective of the problem. If you do it Shigley's way, for every kind of problem you have to do a slightly different approach. And I'm sure this will drive you bonkers in an exam. If you do it my way, it's a very simple thing. Ignore the tips of the beam. Anything in the middle, we have to account for. Okay? So let's see if we can do this. So in our case, I don't care about this and this. So my distributed load function looks like this. Goes 0, 0, 0, 0 like that. It jumps up, goes like that. But please remember, loads are negative if they are pointing down. So it's actually jumping down even though we are drawing up. It's one of those problems, so please be careful. So, try your hand. What do you think is the singularity function for this? So, pause it, try it, and then you will see what I write. Then you can compare. So, I got Q of x equal to x minus 0.5 to the power 0 times 1 kilonewton per meter. You get this? Good. Actually, the rest of the stuff is really straightforward because after this, we are just going to pretend that this is exactly the same like the previous cases. We are just going to integrate as if this is a regular polynomial. That's all we have to do. So what it means is that I get dv dx equals x minus 0.5 to the power 0, which means d equals x minus 0.5 to the power 1 plus v naught. Then I integrate this again. M equals x minus 0.5 to the power 2 plus v naught x plus m naught. Theta equals, sorry, this was divided. Theta equals 1 over 6. Sorry, 1 over 6 EI. You know what I'm doing here, right? This comes from dm dx equal to v. This comes from d theta dx equal to m EI. So I'm just doing the same thing. Notice that my integration looks exactly like the previous case, except that brackets are still retained, the curly sharp brackets. I'll show you how that works. And then the last one is dy dx equal to theta. So this means theta, so y equal to one over 24 EI that's like 1 over 24 EI x minus 0.5 to the power 4 plus V naught x cube over 6 plus m naught x squared over 2 plus theta naught x plus y naught. So as usual, we have 4 constants. I'm going to highlight these 4 constants. There's one, there's the other, there's the other, and there's the other. How do you find the 4 constants or boundary conditions? Tell us. So boundary conditions will tell us at x equal to 0. What happens at x equal to 0? At x equal to 0, we have built-in or fixed, which implies y equal to 0, y at 0 equal to 0, theta at 0 equal to 0. That's easy. So if you go up here, what happens is, how do I evaluate? So y at 0 equals 1 over 24 EI times 0 minus 0.5 to the power 4. Not 0 minus 0.5 to the power 4. Remember, this is angled brackets. This is the only thing you have to remember. What it means is that you don't care about the value of x if it is less than 0.5. It's always 0. So we don't really care about it. So since x is less than 0.5, this thing is 0. That's the role of this angled bracket. So I want you to realize that that's where this angled bracket business comes in. Okay, so then I will get plus, this thing is 0, plus 0, plus 0, plus y naught. So I will get y naught equal to 0, just like before. I'm sorry, boundary conditions were, that's correct, it's not fixed. Go pin. So y equal to 0, that's what I get. And then for a pin joint, moment at 0 equal to 0. This gives me, let's go up here and I'm calculating moment at 0. Again, notice the angled brackets. So that's something that I'm going to highlight because I wanted to see that the angled brackets are retained. So whenever I write an angled bracket, so I want you to realize that whenever I write an angled bracket, whenever x is less than the begins at point, it is 0. So if you look at the moment, if x is less than 0.5, it doesn't matter. So I will get v naught x I will get m naught equal to 0. Hey, that's nice, right? Just substitute it in there. Then let's see. Boundary conditions at x equal to L. I got y of L equal to 0 and m of L. How do I compute y of L? That turns out to be, put x equal to 1 because that's L. L is 1. So this gives me 1 over 24 EI 1 minus 0.5 to the power 4, which turns out to be 0.5 to the power 4. This is 0.5 to the power 4 because x is greater than 0.5 plus v naught over 6 we already knew that m naught was 0 plus theta naught, we already knew that y naught is 0. Then the next one, that's what this gives us. This one will give us x minus 0.5 whole squared over 2, which is 1 half x 1 minus 0.5 whole squared plus v naught immediately it will tell you that v naught equals minus, so 1 minus 0.5 whole squared is 0.5 squared is 0.25 divided by 2 is 0.125. You can take that, plug it in here and solve for it. Please try it. I want you to understand that the best way to do it is for you to complete the full problem, which means that I just tell you find this. That's not time, that's not an indication for you to abandon it, that's an indication for me to stop. You should actually continue and finish this problem. Part of the reason why we want you to do it is again for you to gain some practice. And you should have a moment where you say, aha, I got it. Okay, so that's why we ask you to keep doing this. You see the process here? So I hope you understood how this works. Let's try something more ambitious.